Okay, good afternoon, everyone. We will have areas under curves for this session. I hope you have already studied the subject so that when we discuss, you will have no hard time, okay, understanding the discussion. Let me just start by giving an illustration, but before that, does anybody know how to get the area between two regions? Anyone? Anyone? How do you get the area between two regions? Say you have a curve F and a curve G. And you want to find the area of the region between A and B. This one here. Anyone? Can you give a formula? May want to unmute your microphone. Make sure your microphone is muted. Right, I did not set it in the settings. Fundamental theorem of calculus, yes, but I want the formula using integrals. Okay, integrate the difference of the functions. I see what you mean. So the formula actually is given by the integral from A to B of the difference of the functions, higher minus lower function, with respect to x. And the proof for this formula is the formula for the area under a curve, right? Remember, if you have a curve, say F, and you want to find the area below the curve above the x-axis from A to B, which is this region, the area is given by the integral from A to B of F with respect to x. And you can think of this region here as a difference of two areas. The region, right, under the curve F minus the region under the curve G, right? Now the area under the curve F, which is this one, this whole area here, is given by the integral here, integral from A to B of F. And then the region here, the area of this region is given by the integral of G from A to B. Okay, so it's this area minus this area, which is given by this. And then we can just apply the properties of integrals, right? Which states that the sum or difference of integrals equals, or rather the integral of a sum or the integral of a difference equals the sum or difference of the integrals. So we can rewrite this one simply as integral, or one integral A to B, integral from A to B of F minus G. Now let's see that in action by considering this region in example 1, which is the region bounded above by this parabola y equals x squared plus 1, and bounded below by this line y equals x, bounded on the sides by the vertical lines x equals 0, x equals 1. Now let's, of course, before you can answer the problem, you have to sketch a graph of the functions and then determine the region. But skipping that part, well, anyway, this is just a parabola, right? Which is the translation of the parabola y equals x squared. You move this 1 unit upwards, you get the graph of this one. And then this is just, of course, y equals x, the line that makes 45 degrees with the axis. The other one is like y equals x squared plus 1. But let me show it to you. So there we have it, just that region from 0 to 1. Although this should extend here, this one here. But we are only interested from x equals 0, this vertical line here, up to this region bounded by this vertical line here, x equals 1. So we're looking for this shaded region here. Now using the formula, okay, just given a while ago, what we do is subtract the upper function or the lower function from the upper function, the lower curve from the higher curve. This is the higher curve. This is the lower curve, or line rather. So we have the integral of x squared plus 1 minus x. So this is your f of x. This is your g of x. F of x equals x squared plus 1. G of x equals x. And you subtract the two functions. This is the higher. This is the lower. If you have it differently, if the one curve which is supposed to be the lower curve is the one you put, okay, for the higher curve, and vice versa, you will get a negative result. Although the numerical values are the same if you take the absolute value. But of course, in the solutions, you are required to set it up properly. So say if you have it like this way, then you'll get a deduction, although you'll get the same numerical result disregarding the sign. But this is the correct setup. Now, of course, you have to put in the proper limits. We are only considering from the region from 0 to 1, so those will be your upper and lower limits also from 0 to 1 of this integral. Okay, so that's with respect to x. Of course, there should be a dx here, but if it's understood to be with respect to x, then you may omit writing that symbol there, which reminds us we're integrating with respect to x. But I'll put it in the second line here. So simplifying gives x squared minus x plus 1, 0 to 1. And we just have to evaluate this integral to get the exact area of that shaded region there. So we have x cubed over 3 minus x squared over 2 plus x. Then we put a bar, and then the lower and upper limits. We substitute the upper limit first. So we plug in 1. And then we plug in 0. Then subtract. Of course, this is just 0, so you may want to omit writing that and just give this one, and then simplify. So that's 1/3 minus 1/2 plus 2. Okay, which is, okay, 1/3. We can write this as 2/6 minus 3/6 plus 6/6. So we have 5/6 square units. Or you can use your calculator to simplify that for you. And then encircle or box your final answer. So this is 5/6 square units, without using a ruler or approximation or whatever measuring device to get the area. Use calculus. Now, sometimes, I'm not sure if this will be included, but let me discuss it anyway. sometimes you will not be given the lower and upper limits, okay? As in the previous example where it's given that the sides are bounded by the vertical lines x equals 0 and x equals 1, which makes it easy for us to put the lower and upper limits in our setup, in our integral. But if you look at this example here, you are only given the curves y equals x squared and y equals 2x minus x squared, and those are parabolas, and you are not given the sides, or rather the bounds from, say, x equals this to x equals this. And when that is so, that means that the region in consideration is enclosed, as in the state given by the word there. The word is given there, enclosed, so that these two actually bound the region. They serve as already the sides, right, that encloses the region. But in order to see how the region looks like, of course, you will have to sketch those parabolas, and we discussed how to sketch parabolas last Math 30.15, right? Where you find the vertex, the intercepts, and so on. Then you have to determine if it opens to the right, to the left, or upwards or downwards, and then you have the sketch. Okay, you just connect all the points available. Or you can use the tools of calculus, of course. When we were discussing the graphing strategy, right? You get the first derivative, second derivative, but since these are just parabolas, it's enough to just find the vertex, then perhaps the intercepts, and then whether it opens up or down, or to the left or to the right. But skipping that part, let me just show you the graphs. Okay, so we have there the graph of y equals 2x minus x squared, which is this purple, or what's that, pink curve, and then the blue curve is, of course, y equals x squared, obviously. So we see which one is above the other by graphing. Of course, you won't be able to tell that if you don't have the graph. So in the setup, you might eventually put a wrong higher function and a wrong lower function. You might end up switching the two. So you have to show me a sketch of the region, because that merits points, and so that I see that you understand what you are setting up, okay, for your area computation, the integral itself, I mean. So given the graph, of course, it is now easy to set up the integral. But of course, since the graph already gives us the intersection points, we can just set it up. But to find the intersection points, of course, you have to use algebra first. But we will just show that after the setup of the integral. So suppose that you know the intersection points already to be 0, 0, and 1, 1. You will just be writing, okay, the following integral. You look at the x coordinates, of course. So we're integrating with respect to x, so you will have to use the x coordinate. So the x goes from 0 to 1 for this region. So those will be your lower and upper limits of integration. And then higher curve minus lower curve gives us 2x minus x squared minus x squared. Okay, with respect to x. Simplification, we have 0 to 1 of 2x minus 2x squared with respect to x. Integrating, we have x squared minus 2/3 x cubed, 0 to 1. Now, notice that since the lower limit is 0, we won't have a problem calculating that, so it's just 0. So let me just plug in 1. So we have 1 squared minus 2/3, 1 cubed. Then of course there's a -0 here supposedly. So we just have 1/3 square unit. Now, of course, if you do not know the graph, you won't be able to tell which is the higher, which is the lower. And also you won't be able to put the proper lower and upper limits. But by graphing, you can tell which is the higher, which is the lower. But to get the, of course, points of intersection, you have to solve for that. You won't be able to tell them immediately from the graph. So let me now show how to get the points of intersection. Of course, you're just solving a system of equations here, which you did in Math 21, if you took Math 21. But anyway, this is not a difficult system to solve. Since y is given directly in terms of x, you just have to equate the two. Or rather, let me just write that as 2x squared minus 2x equals 0. So we get two possible points of intersection indeed, x equals 0, and then you solve for the corresponding y values if x is 0. So plugging in here, or you can use this one, of course, but I choose the simpler one, y equals x squared. So I plug in, so I have 0 squared, so y equals 0. If x equals 1, so y is 1 squared, y equals 1. And thus we get the points of intersection 0, 0, 1, 1. And then sketch the graph, right? And then just use the x coordinates to put the lower and upper limits for the integral. Any question? So I want you to try one more example, sorry, before a sit work. By the way, since I think due to the discussion by Sanggu, tama ba Sanggu yun? Instead, in order to lessen the strain on the students, so instead of having like live or synchronous sit work, we will just have like a take-home sit work sort of, or rather a homework, which may be submitted within the day. So instead of like having just 30 minutes, right, to answer, and you have to, log in within the given time period. So you have the whole day whenever it's announced, okay, to answer the homework. But of course, there will still be a time limit once you start answering the homework. But let me do this first, then the sit work, which is not graded. Find the area of the region bounded by the curves y equals sine x, y equals cosine x equals 0, and x equals pi over 2. Now you have to review, of course, the graphs of your trigonometric functions. You can do this, of course, by using point-by-point plotting, or just by memorizing the graphs, okay? Or for now, okay, you can use a graphing calculator, but not, of course, in the exams. So with skipping the part of graphing, I'll just show you the graphs over 0 to pi over 2 of those curves. We have this graph. So you see that since you're given the boundaries x equals 0 and x equals pi over 2, but from 0 to pi over 2, you see that there are two regions, A1 and A2 in the figure, so that you cannot just like set up like cosine x minus sine x, and then from 0 to pi over 2 already. Because in one region, the one curve is higher than the other. In another, it's the other that's higher than the former, okay? So we will have to split the integral here, okay, into two integrals, which give us the area for each region A1 and A2. So let's set up the integral for a sub 1. And in this region, it's cosine that's higher than the sine. So we will have cosine x minus sine x for our integral. And then our limits will go from 0 to pi over 4 based on the graph, of course. How did you get pi over 4? That happens when the two intersect. And that means sine x equals cosine x. And we know that the sine and the cosine are equal when the angle is 45 degrees or when the real number is pi over 4. Okay? So that means we will have to use for the upper limit of this region, pi over 4. Okay? The region extends from 0 to pi over 4. And then the other region from pi over 4 to pi over 2, so those will serve as the limits of integration. So we have a plus. Now this time, it's the sign that's higher. So sine x minus cosine x from pi over 4 to pi over 2. And there we have the proper or correct setup for the area under or the region in consideration. So of course you get like more than half of the allotted points for setting up the correct integral or sum of integrals. But the next would be, of course, the correct evaluation of the integrals, which takes some work. So let's do that. So let's start with the first integral here. We know already the antiderivatives of the cosine and sine, they are each other, although for the sine, okay, it's the negative cosine. So integral of cosine is sine, because the derivative of sine is cosine, right? The integral of sine is negative cosine, but since there's a negative, so plus cosine. Same thing. We have here plus, okay? This one here, integral of sine is negative cosine. And then integral of cosine is sine, so we have minus sine. Okay, from, again, pi over 4 to pi over 2. Okay, so let's evaluate those quantities. So for the first part, we have sine pi over 4 plus cosine pi over 4. And then we substitute 0, and 0 has coordinates. If you still remember this, what they call this topic on the derivation of the trigonometric functions, spatial angles like 0, pi over 3, pi over 6. So you just have to look at the coordinates of on the unit circle. Then this will be cosine, the x coordinate. Then for the y coordinate, that will give you the sine value. So sine 0 is 0. Okay, let me just put that already here. Sorry, it's a minus. So sine 0 is 0. Cosine 0 is 1. So I plugged in 0. Okay, we have this. Then it's a minus outside. And then plus the second part. So plugging in pi over 2, the upper limit first. We have, okay, negative cosine pi over 2. And pi over 2 has coordinates 0, 1 on the unit circle. So cosine pi over 2 is 0. Sine pi over 2 is 1. Then minus, of course, because it belongs here for the second part. Minus, plugging in pi over 4, we have negative cosine pi over 4 minus sine pi over 4. So we simplify this one. And in fact, we'll have just by distributing the negative, we have positive. So 2 sine pi over 4 plus 2 cosine pi over 4. And then minus 1 plus minus 1. Okay, so sine pi over 4 and cosine pi over 4 are each equal to square root of 2 over 2. You can use your calculator to determine that. You would just evaluate this. Okay, and if you wish, you can give the approximate value of that. So it's 0.83 approximate to correct to 2 decimal places. Square units. So I want you to try this out. You have to sketch, okay, and then set up the integral. Okay, let's see. So if you have sketched the region correctly, so this is y equals square root of x. Then you have your x squared minus 6x. Then you have 2 to 4. So this is the region you're considering. And you want the area of that. Okay. So it's just the higher curve minus the lower curve. Limits 2 to 4. Then just evaluate the integral. Now this time you don't have a zero on the for the lower limit, so you'll have to calculate both and subtract. Okay, this is exact. So a perfect square. So square root of 4 is 2, 2 cubed is 8. But this one is not. So you'll have to leave it as in radical form. This is just 2 square root of 2. So we have okay, the over the 3's. So we just add or subtract their numerators. Don't forget you have to distribute the minus sign. You have to be very careful with the numerical computation. So 16, this should be plus 8. So 24 minus 64 is negative 40. 48 minus 12 is 6. So we have 9108 minus 40 is 80. 68. Let me approximate that. Okay, so 20.8 or 7. Use 2 decimal places. Okay, so Mr. Roque's answer is correct. Also, Ms. Mendoza's exact answer there given in the chat. Okay. So that's it for today. So we'll have another sync session on Thursday.